Hey, let's get this show on the road. All right, metal casting. Keep up with this. Welcome everyone. We're back with another integrity session here. Metal casting, a little of the demographics from our American Foundry Society. Currently 2,000 metal casting facilities in the U.S. In 1991, there were 3,200. In 1955, there were about 6,100. So you see it's kind of gone down a little because of the labor that's involved. And we'll show you the different types and what we're doing to change that. 80% of the firms are small businesses, less than 100 employees. There's still over 200,000 people that are employed by the U.S. metal casting industry. So that would be more than the people that live in Longview and Tyler combined. Maybe add Kilgore in there, you'll be okay. 90% of all manufactured goods contain some metal casting. The global leader in casting application is the United States, and second in production. Used to be number one, but like I said, it's labor intensive, so it's gone elsewhere. It's kind of dirty and nasty. People don't like to do it. I know when we used to visit, Alamo Iron Works, and watch them cast things. I mean, it's interesting, but geez. If you have to do it for a living, it's kind of dirty, and you get all that soot and nasty stuff and those little speckles on your car in the parking lot. In the U.S., you are rarely more than 10 feet away from a metal casting. So what they're saying there is we use a lot of castings in our everyday lives. Now let's see what our production chart is now in 2011. It's pretty recent for these things. Yes, where there's cheap, inexpensive labor, China. And it's big, and it's a big country, you can pollute a lot. But what they're finding out now is that it's getting so polluted, people are getting sick with their job. I was reading the Business Week, and a lot of people are moving out. They've made their money, it's enough to live off of, and they're moving back into the country again to get away from all the filth and pollution. Kind of interesting. So they'll be getting all those scrubbers and all that other stuff to clean up their act, clean up their rivers, all that stuff. It's going to cost them money and everything else. The next thing you know, it'll be cheaper again to make it in your own country. So, and we're already getting that way with the value of our dollar because they keep printing money all the time and they keep the interest rates low. So they never have to, so they wouldn't have to pay it back with the interest. So, anyhow, that's why our interest rates are so low for banking, because they're going to have to pay back all these loans when you're, what now, $17 trillion in debt and growing, maybe more than that. U.S. 12%, India 12%, so hey, look at that. Japan 6%, Germany 6%, so you look at these, Brazil 4%. Brazil's a powerhouse when it starts coming to manufacturing now. Korea, as you know, all the Korean electronic stuff. Italy has a lot of manufacturing. I know I used to work at a few different places, and you'd see a lot of machine tools from Italy. France, I guess, I don't know. Anyhow, France is different, but we always have to thank France, because without France, we wouldn't have won the Revolutionary War, would we? And in fact, the War of 1812, the British were fighting the French. And thank goodness they were having so much trouble that we were giving them so much trouble. And they had to take care of the French because they were right there across the shore. So they gave up on us. That was good. They did burn down Washington, D.C., but other than that... Okay, 12 million if you look at tonnage of castings produced in the United States, so still a lot. $30+ billion industry, so that's a lot to our GDP. All right, anyhow, Casting, metal castings takes place when liquid metal is poured or otherwise forced into a mold. The metal cools and solidifies in the mold, taking on its shape in every detail. Casting processes make it possible to produce metal parts rapidly and economically. What's good is if you can have a shape and it can fit into that shape as well as possible, that's less machining you have to do. If you can get the shape exact, that's better yet. Then you're done. Maybe you have to polish it, maybe you don't. And so that's the deal, is it saves all these other processes that you have to do. And speaking of the American Foundry Society, if I got that right, they had a little documentary about metal casting. It shows a lot of the different processes in it. It's only a few minutes long, so I'll show it to you here. Hopefully it'll work. Let's see. Well, maybe not. I don't want to wait all day. I don't have time for this. I guess, no. It's got all these other castings, which we'll show you later. I've got some. But geez, you play that once and then you can't get it again. Boy, that's interesting. So anyhow, I'm not going to worry about it. Let's go back to what we were talking about. I can show you that later. But the main gist of it is they'll show you these different, and we have a lot of robotic arms now that help move all this stuff and save time, and so people aren't exposed to all the nasty stuff, and we can make things quicker and all that. And that's why we teach all this automation now in our curriculum, because that's where it's all headed. All right, parts made in the manner are called castings, so that makes sense. A factory that specializes in making castings is called a foundry. Of course, all this stuff will be on the quiz, so you should pay attention. The 6 main types of castings are, and there's more than this, but these are the main ones. Sand casting, they call it green sand because, you know, it's not totally cured and set up. So it's not really green in color. You'll see that it looks like red clay. Shell molds, permanent. Investment casting, which has been around forever. Plaster, you know, you use gypsum, that white plaster, and it gives you a nice smooth. And then die casting. So you want to speed it up and do some die casting with the different pot metals. Metals that melt at a lower temperature. Alright, so the different equipment, again, I think I asked you all these. I give you the definitions, you have to tell me what it is. Let's see, a mulling machine is used to thoroughly mix and recondition sand prior to making a mold because it clumps up, so you got to break it back up so it's not all clumped up. And then you riddle is like a wire mesh, you know, wire screen sieve that is used to separate the big chunks of sand from the smaller granules. And I'll show you a video so you'll understand what this is all about. So that's a riddle. Riddle me this, Batman. Okay. So anyhow, why don't they just call it a sieve? Yeah, I don't know. Flask is the frame that holds the mold. There's 2 halves of the mold. There's the top part and the bottom part. The top is the cope, and the drag is the bottom. And you can remember that because you're always dragging your arse, right? So that's the bottom half. And cope, you have to cope with things, you have to use your head, so that's the top half. So you should get that right on the quiz. Let's see, we just said that. Pattern is a wood or metal representation of the part that is going to be cast. So you have this pattern and it's cut in half because you'll see when they do the 2 molds and then you pull them out. So then when you put the 2 mold halves back together, see, that way you can take out the pattern. Then you have a hollow cavity, and that way the molten metal will go into that hollow cavity that was created by the pattern. And you have to have some type of draft angle or you can't pull out that pattern if it's perfectly square. And you'll see what we're talking about in a minute. Then you have a shrink rule. Is that a rule that has shrunk over the years? No, what they're saying is when metal's hot, it expands. So you got molten metal. Then you pour it into your mold there, And what's going to happen? Well, that metal's going to cool, it's going to shrink, and depending on the metal, it shrinks so much per inch. So there's different shrink rules. One is for every foot, it's an 1/8 inch bigger. And one, it's for every foot, it's a 1/4 inch bigger. So that way you're intentionally making your pattern bigger than it really needs to be because the metal's going to shrink later. So anyhow, that's what a shrink rule is. It's taking in consideration how much it's going to shrink. All right, then your parting compound is a fine powder, like talcum, something like that. There's different types we'll talk about. That is used to keep the molding sand from sticking to the pattern. You'll see in these videos they pour that white like talcum powder. And it just, because you'll have those two halves and you don't want them to stick together until you pull your pattern out. All right, then you have the rammer. And there's ones that are pneumatic rammers, and you just do it by hand with a rammer. It's used to pack sand that has been riddled into the pattern, and riddled is that screen, that sieve, so you're getting all the clumps and chunks and garbage out of it. This makes the sand firm enough to hold the shape. The green sand is kind of like like a bentonite kind of material, kind of a clay. And then you add so much percentage of water or oil, depending on the type. If you add too much, it causes it, when it gets hot with water and moisture, makes explosions, and that'll pitch your casting that you're making. So I think we mix it, I forget what it is, with the oil that we had. We bought the stuff, and then we would mix it back up again. It's been a while. We don't have a foundry here yet, and so you forget. But anyhow, this makes the sand firm enough to hold the shape of the pattern while the molten metal is being poured into it. All right, and then to keep your pattern, because you're going to have one half and the other half, we'll show you how you put them together. There's usually alignment pins in the pattern, so it's not cockeyed and off, which I've seen people do. They try to make it quick, and then that means then you have to grind and machine all that stuff down later. No, you don't want to do that. Then you have a gating system. You can't just pour it right into the mold. You've got, a sprue, and the riser, and all that gating system. And the reason you have that is with any type of metal, there's impurities and junk in it that floats on the top, slag and all that stuff. Just like in welding, we talked about slag. And so when it gets really hot. And so what happens is it'll go in there, it'll go into your mold, and all the impurities want to rise up. So then you have that riser, and then all that junk's up there, and it's away from the actual part that's in the middle. Yeah, you have to cut off these parts later, but that keeps all the impurities and all the junk out of your precious little part that you're making. So anyhow, then you'll form a pouring basin, because you'll notice with the ladle that holds that hot molten metal, it's hard to get it exact when you're pouring that. You want to stay away from that heat and the flames and all that. And you'll see they've got these like tongs and holders holding that ladle and pouring it to people. Or if it's a small amount, you can do it with that. But again, you don't want to get real close to it because it's super hot. And if it splatters and all that. So you don't want to get that all over you. I don't care what kind of leathers you're wearing and what have you. It doesn't feel good to get burned with molten metal. And then, so you have that kind of tapered. Then you have the sprue that goes down into where your pattern's going to be. And again, this is all stuff that you have relieved. You've removed that sand out of your mold, so that way you got a place for all this stuff to run into your hollow cavity that was created by your pattern. So the sprue is a square, well, it's usually square in cross section and tapered to reduce turbulence and prevent air from being drawn into the cavity. And it seems to work better than just round. Now you'll notice when these guys are doing it, they're just using a round pipe and all that. They're not going to make a square section, and that's fine for what they're doing. The runner then from there delivers the molten metal into the cavity, which right where it comes in, enters, is considered the gate. And then after it fills up the cavity, then the metal has to go somewhere, or all the impurities would stay in there, and that would destroy the quality of your part. So then it rises up. Plus, when it rises up, then you know you filled up the pattern totally, your part, when you see the metal coming up. If not, you wouldn't know if you filled it up or not. So, or also you could get an air pocket in there. The air doesn't come out, and so you get half a part that's formed. Some of us has had that problem when they were working with plastics projects and stuff like that. So we had to vent the air out. I had to machine those molds a little more and get more air out of the molds so we wouldn't have that issue. Alright, so our green sand casting, here's the top half, the cope, and the drag, the bottom half. And then you have the flask that holds the whole thing together. And then when you do all the flipping and all that to get it all aligned, and then you can remove the flask, and then you can make some more. Then you can get all these made and then pour them all at the same time. Okay, and here's your actual casting in there. Yeah, I'm sorry, here's your molten metal. What they did was they put a core, which is also made of sand, that they're going to break out later, and that leaves a hollow cavity, so that way you don't have this big, heavy piece of metal, and you use it. You know, metal's expensive. You don't want to waste it. If you need to make that part lighter, you don't want it to be a solid piece of metal. Here they are pouring it. Here's the crucible. You know, flask if it's smaller, and they're pouring it into the actual flask, which is the holder for your cope and your drag. All right, so the crucible again holds your molten metal and pours it. After you've heated it up in your furnace, you can have electric furnaces, you can have gas furnaces, you name it. There's all different types of foundry setups. All right, but again, the crucible holds your, and the flask holds the two parts of your. I keep thinking flask. I'm sorry, I get confused sometimes. I think of a flask as, you know, something where you have a nice liquid that helps the day go by, and you have a flask hidden in your coat pocket, sport coat pocket, and then you take a few swigs in that. And so, no, that's not. That has the mold, the liquid in it. No, the crucible does here when we're talking casting. All right, and you pour your molten metal from it. So, sorry about that. Anyhow. Yeah, here's a good side schematic view of this. Here is your crucible pouring the molten metal. And usually they'll have a pouring basin. So when you first pour, it comes out, you know, it may smash the sand and do some damage. So it goes into there, then it comes around, comes down the sprue, which is tapered, and then you see, you know, that pocket too, because when it comes down, it's going to initially want to take a chunk out of that, excuse me. So then you have the runner, and then where it actually enters into the part is the gate, you know, like the gate to get into a house or into your backyard, whatever. And that's your actual mold cavity that was made from the pattern that you removed. And then your riser, and then when you see that molten metal coming up on top, you know, hey, stop pouring it and pour the next one. And again, there's your pattern. See the alignment pins there. And they're just put together. Then you have to take these apart, take out the pattern, and then put it back together again to leave the hollow cavity. But while you're doing that, that's when you also dig out these gates and runners and all that stuff, your whole gating system, which they'll show you in the video clips. All right, keep moving here. All right, let's see this one. This one is, I think, in the University of Memphis or one of those places. They have they made a YouTube thing, so it's pretty good. You'll see a few things that are out of whack, but it's okay. And then this one shows you a place where they have some more equipment. It makes it easier to make a sand casting. So let's see if this works today. Hopefully. All right, let's see. Boom, boom, boom. Yeah, here's their furnace, a gas furnace. Oh, they've got music here. There's their precious little part that they're going to make, but that is their pattern. Now, they're supposed to keep that straight. But anyhow, they usually you put it down with a little of this material to keep it straight. But that's okay. And they put that compound around it, so the mold release, I guess. And see, here's the riddle. And then they've riddled that in there. And see, it's not really green sand, okay? They screed it off to make it flat there. They're melting whatever scrap they had left over. Okay, and there's their pattern. They're putting some more, so that way it won't stick. They're riddling in the green sand. As you can see, it looks more like clay, but it's sandy. But usually they have an oil binder to it. And see, now they're making their pouring basin and their sprue. And there's their riser. And they take them apart. They're going to take out these patterns. But first, they're making, what, a gating system. So the runner into it, and then it just goes right in, and then they have to press that down so it's going to come apart on you. You'll get it ready. And you always have a piece of wood or something under it. Same for, you'll notice when they put down their crucible. You should never put a hot crucible down on concrete, because concrete is cold. And the heat and the cold, what happens to concrete? Concrete explodes. So I got lucky here, but I don't know if I do that. Maybe it's treated with something, but you just don't. Oh, I see it's got a metal piece under that, but still, that's pretty hot. Pouring the aluminum in there. See, then there's the rise that filled up. And he's got sneakers on. Is that a wise choice? They do have these covers, but still, I would have more protection. Everybody always wants to take it out real quick. Your best bet is to, if you can, let it gradually cool, and then the molecular structure and everything, and it's good. But they're just showing you how it all works. There's all this gating system that they'll have to cut off. The riser and the... A little too much music there. Alright, but anyhow, there was their pattern, and then there is their actual part there. So not bad, it came out good. Then they're grinding it all down, sanding it all down, make it look nice. I don't know what they're doing with it. Hopefully they're making something with it. But anyhow, enough said there. Alright, so we'll make this smaller here. Let's get back to reality here. Alright, and the other one you will notice, you will see they have some equipment that makes the life a lot easier.
This video shows the sand casting process to make a mold to produce aluminum castings. This particular item is a handle for a snake catcher.
A snake catcher?
The match plate makes 4 handles at one time.
Isn't that nice?
Once the match plate is set between the 2 halves of the wooden blast, the molder dusts a non-silica parting on the pattern so sand won't stick to it. To get only small particles of sand against the surface of the pattern, he riddles moist sand, which is coated with bentonite clay.
Yeah.
The clay bonds the sand grains together so the block of sand will not crumble.
There you go.
He uses an air rammer to compact the sand.
That's much better. Better setup here. Now this is a better sand where it's got the bentonite in it.
To further compact the sand, the jolt squeeze molding machine jolts the mold.
Yeah, there's a
It
jolt.
sets on a bottom board which will end up underneath the mold.
Yeah. That way they don't stick. He's riddling it in there. Oh, this guy loves
To make
his
the
job.
top half of the mold a cope, he repeats the process, parting dust, riddling facing sand, and compacting backup sand.
That way he
He
gets.
sets a squeeze board on top of the mold. The jolt squeeze machine pneumatically squeezes down on the squeeze board and up on the bottom board to further compact the sand.
Can't beat
The
that.
top squeeze board left a depression on top of the mold for a pouring basin.
Yeah, look at that.
The brass tube, which is pushed down to the match plate, cuts a sprue passageway for molten metal to enter the mold. An air vibrator attached to the match plate helps prevent sand from sticking to the pattern. When lifting up the cope, or top half of the mold, alignment pins on both sides of the flask
Yeah. Oh, sorry. Keep going, keep going.
allow a perfectly straight lift.
Yeah. Yeah, because if they get crooked, like I said, it throws it off or it breaks off the sand. So then he's cleaning out all the rest. He's got compressed air there. Yeah, this is set up just to make casting.
The same alignment pins guide the match plate when it is lifted.
Kind of vibrates a little and gets it up, and it's got air again, compressed air. He cleans it out, and then notice here. They don't want to make those handles solid metal.
Each of the
It'd
four
be too heavy.
castings, snake catcher handles, has a slot for a trigger. This slot is formed by setting hard resin-coated shell cores in the mold. Where there is a core, metal will not fill the space, hence a slot.
Yeah. You don't waste all that metal. And then it's lighter.
By the same token, any loose sand in the cavity will prevent metal from completely filling the cavity and will cause a dimpled surface. Blowing away loose sand before pouring the metal is very necessary. The two halves of the mold, cope and drag, are aligned by the flask guide pins. By unhinging the flask and removing it from the mold, the flask is ready to make additional molds.
There. See, when he does his pour, he's got a whole bunch of them he can pour at once. All right, enough said there. All right, so that kind of gives you an idea what is all of this mess about. All right, sorry about that one. Okay. Anyhow, let's get back to reality here. All right, so sand casting in general, and again, there's sand in there, so you'll notice that it's rough, the texture. Like if you look at castings to our machines and that, they kind of feel rough because they were sand castings, because it's the quickest and easiest way to make those parts as fast as you can. But it does have a rough texture, and usually that's good, doesn't matter. And if you want, you can machine it later if you want it smooth, but in most cases, you don't have to if you're just making a big base for a machine. All right. Utilizes gravity to feed molten metal into a non-reusable mold, as you saw what we did there. Because the sand. But then you can break up that sand and you can reuse that sand again. Sands contain binding materials. We talked about the bentonite and the oils in them. Requires a reusable mold pattern, which you can pull out and then leave that cavity. Produces a parting line on the workpiece. And the parting line is where the two mold halves would go together. It's going to be a little, just can't help it. Requires drafts. You have to have draft angles, or if not, you can't pull those patterns out without breaking off some of the sand and everything else. Produces rough textured surfaces, because sand is rough. And sprues, risers, runners must be removed later. You cut them off and then you melt them down and you can use them for the next one. And again, that jolt squeeze turnover machine, you saw that in action in the last video. So that's what they're talking about, how all that worked. just makes your life a lot easier. Really compresses it perfectly versus somebody there with a stick trying to get the same equal force. And what that does is that's putting pressure around your pattern so you don't have loose sand around there, because then when you take them apart, you may have a part where it didn't compress the sand enough, and then that's going to make a bigger area because that's going to fall out, and then you have a bigger casting than you need, and you got to grind all that down, machine it all down and everything. So that's why that's important, and if you do this for a living, yes, this is nice. Showing you the depth of a wall in inches. So depending how deep that wall is, then you have to have a certain draft angle. Okay. So if it's 7 inches, you know, it's long enough that you can just have 1 degree, but that'll show up over 7 inches. If it's just 1 inch, yeah, you need more of a draft, or you're not going to notice it. You need more of a 5 degree. That's all. I mean, it's common sense. Your eye would kind of see that too. All right, and different types of patterns, you know, because you're going to remove them. It can be wood if you're just making a low production, because, you know, the wood will wear down eventually if you're making a lot of these. Metal, aluminum, you know, iron, steel. You can also make, if they're really complex in that, you can make plastic epoxy resins. Again, this stuff is going to be pulled out. A lot of times we can make molds out of flexible plastic, and then not have to worry about draft angles, and then just bend the mold, the plastic mold, and pop them out. But again, we're not talking about that here. We're talking about sand castings. These are usually typically for bigger, large parts and what have you. Shows you the amount of shrinkage, inches per the foot of the material. So if you look at this, you got 1/8 of an inch is what? 2/16. 5/32, let's say that's 4/30 seconds, would be 2/16, so it's a little more than that. So 2.5/16, right? And then 1/10 of an inch to 1/8. All right, and then cast steel goes up to 1/4, so which is 4/16. So steel shrinks the most here. And percent yield, which is kind of interesting. That's why you see a lot of things, a lot of metal parts are made out of cast iron. 80 to 85% come out good. Steel, it's 50 to 60%. So it's kind of the lowest of the bunch, isn't it? Yeah. So it's interesting. Process capability, accuracy of patterns, including the cores and inserts, is going to then, if it's done well, then that's less you have to machine later. You have to worry about casting shrinkage, so you got to make sure you got that shrinkage under check. Pattern smoothness, how smooth your pattern is, but you still have got sand to deal with, so you're still going to have some rough parts there. The pattern wear, how far is it worn down? And after a while, that's what happens when you buy parts. So, gee, this doesn't fit. It's either too small or too big, because that pattern wears out. They're making thousands of these things somewhere in China or whatever. And after a while, it wears out, so that's allowing the part to get bigger and bigger, and or smaller, depending on which way the casting's going. And then it doesn't fit the other part right, and makes for a mess. So anyhow, and then your gating and rising system, depending on how well you have that, if you're getting enough metal in right and correctly to fill up that cavity before that metal cools too much. So it's amazing how the gating and rising systems work, and how the craziest looking ones seem to work the best. It just really doesn't make sense sometimes. Cord sand castings, again, that's for when you make actual out of sand as well, the cores, those hollow cores that are going to go in there, well, they're not hollow, but it's going to make it to where you're putting that sand in the middle of where that pattern would be, but not the whole thing, not filling up the whole thing. And so that's allowing for hollow parts that you wouldn't have to machine later. For instance, an engine block, you've got that casting, but it's not all one big solid piece of cast iron. They put cores, let's say it's a V8, 4 on one side and 4 on the other side. And then all they got to do is then maybe machine it a little bit and hone it. But all that material is not metal. Can you imagine having to machine all that out? Well, sometimes they do for exotic engines that are made out of certain aluminum alloys. They take a big block of special grade aluminum and machine them all, especially for a lot of those Top Fuel and funny car. But that's, you know, you're making a lot of money off of it. This is something, you know, a car, you got to keep down the prices. People aren't going to pay, you know, 20, 50, 100,000 for a motor. All right. Yeah, this shows you the cores and where they would go in there for where your cylinders are. So core sandings utilizes core sections to form complex molds. Cores are made of hardened or baked sand. Produces shapes unattainable through other casting processes. Is a low production process. Cores are assembled with glue or steel bands sometimes, and can form parts requiring more than one parting line because of the way that all is put together. Then we have no-bake mold casting. So here is a metal process wherein molten metal is poured into a non-reusable mold made from a mixture of sand, quick-setting resin, and catalyst, and held until solidification occurs. What this does is it keeps it all, you're mixing it up, you know, like it's an epoxy in that. And so if you pour this all in there, it's going to form right around whatever it has to, and you're guaranteed a nice, perfect casting. Because with the sand casting, the green sand type, you could still, when you're doing that and moving it around, a piece could break off or something. It's not perfect. But since this sets up just under room temperature because it's got a catalyst to it, you're going to get a perfect casting every time. Of course, it's more expensive because you can't reuse this sand that's set up. I mean, it's done. So it just depends on what you're trying to do. If it's expensive parts with special alloys, you got to pay the price. Or let's say you always have your cores keep falling apart or something, and you want to make them out of no-bake. Hey, that's fine. Same thing. No-bake versus, you know, tells you the reasons for it. It's more expensive, but it gives you better, closer tolerances. It's a finer sand mixture. So it gives you a smoother finish, and again, they usually come out perfect every time versus a sand casting. It's kind of rougher, and sometimes they don't come out perfect. But the drawback is, again, the no-bake is more expensive. Why they call it no-bake is you'll see that we're going to do another process, another casting process, where they heat up the molds or they bake the actual patterns that they make and melt them out of there. There's some ovens involved ahead of time before they use a furnace and pour the molten metal in. So that's why they call this the no-bake. It's where it's mixed with a catalyst. You don't have to heat it up or anything. So that saves money there, but then you're having to pay for a catalyst, which is expensive. So no-bake mold casting utilizes gravity to feed molten metal. And it's the same as the green sanding, except for molding, sand is poured into the mold instead of being rammed. Okay, so that way it's poured, it hardens, it's going to come out perfect. The other one, depending if you rammed it just right and got it all the way around your pattern right, a chunk may fall off, and then you have extra molten metal that's going to be in there later. Molds are chemically cured at room temperature. Again, you don't have to bake these. Dimensions are usually precise and repeatable, reduces labor costs, has high casting yields, and produces less scrap. And that's the beauty behind that. So it may outweigh the cost of all the sand that you're going to have to throw away. All right, shell mold casting. Here's another way of doing something, and obviously there's a shell mold involved here. Process in which molten metal is poured into a heat-cured, non-reusable shell mold made from silica sand and, again, a resin binder here, and then held under solidification until it gets solid. Now, what the difference is here is they took the no-bake and found a way to save money. And what are you getting at here? Well, they have the actual casting that's going to be inside. So what they'll do is they'll take the pattern, and it's usually a heated pattern made out of metal, and then they put it in this one's a dump box of the material. Yeah, it's the same material there. And because it's hot, that sand resin mixture cures certain depth, depending how hot it is and how long you leave it there until it's exposed to the heat, and it makes a certain thickness. Then you take it out, and then you haven't ruined the rest of this material. You can use for another one. Then you just fill it with a backing material, inexpensive backing material of sand that you can reuse all the time. So think about it. Hello, what have we done different here is we're not using as much of that epoxy type sand that you have to throw away. The other one would fill up this whole thing. But you do have to go and heat up a pattern. It has to be a metal pattern. The other one could be a wood pattern. With the mold release on it, you take it out. Here you actually have to machine something that can be heated up and then have this around it. That'll cure around it. Then you take your molten crucible or ladle if it's smaller. That was the word I was trying to think of. I had flask on the mind there. It's getting late when I do these integrity sessions, so I'm sorry. But anyhow, and then we're pouring that molten metal in there. And this way, this is the only part you're going to have to break off and not use. You're not going to reuse that. And then once you break that off, you've got your finished casting. So pattern creations, a two-piece metal pattern is created in the shape of the desired part, typically from iron or steel. Other materials are sometimes used, such as aluminum for low production, or even graphite for casting reactive materials that react the alloys with the steel patterns. All right, anyhow, mold creation. First, each pattern half is heated to about 350 to 700 degrees Fahrenheit. There's your Celsius. And coated with a lubricant to facilitate removal. Next, the heated pattern is clamped in the dump box, which contains a mixture of sand and resin binder. The dump box is inverted, allowing the sand resin mixture to coat, and then it doesn't cure until it's exposed to the heat. So the other stuff will fall off in that dump box, and then you can use it for the next one, so you're not wasting it. Then each pattern, half and surrounding shell is cured to completion in an oven. After you have that part that comes out about ½ inch or an inch, that form, then you heat it in an oven just to make sure it's fully cured. Then the two shell halves are joined together, and remember they're hollow. And then they're clamped together, and then they put that supporting backing material in there, and you're good to go. Then the mold is you pour from a ladle or a crucible in there, and then you let it cool. And then after the molten metal has cooled, the mold can be broken and the casting is removed. trimmed and clean, and you're good to go. Okay, and it's just showing you different types of machines that are involved with this. And same thing. And here's, let's say, several of them. And then you can have the backing support material as something else. And here it is, pouring it in there, and we're good to go. This one looks like it has, yeah, no, this one is hollow. It's going to be one solid piece. This part is our actual mold. We removed the pattern, left this hollow cavity, and then this is the backing material, which could just be green sand. You know, it doesn't matter. So it's superior to other sand casting processes in the duplication of intricate shapes and dimensional accuracy. Processes can be completely mechanized, uses a thin-walled, non-reusable shell made of sand resin mixture, requires a heater metal pattern for producing the shell molds. The Germans came up with this idea in World War II because they couldn't use as much material. At the time, we were bombing their factories with the B-17s and what have you all the time. So anyhow, they came up with a lot of little neat ideas. It was more accurate, so it took them less time to machine things, and so they could make different parts to tanks and you name it. Then we get into permanent mold casting, a process in which molten metal is introduced into a permanent reusable. Here, all the others have been non-reusable, haven't they? But this actual mold we can reuse. And then under gravity or low pressure and held until solidification occurs of the metal that you poured into it. Permanent mold casting is a metal casting process that shares similarities to both sand casting and die casting. As in sand casting, molten metal is poured into a mold which is clamped shut until the material cools and solidifies into the desired part shape. However, sand casting uses an expendable mold which is destroyed after each cycle. Well, it's just made out of sand, who cares? Permanent mold casting, like die casting, uses a metal mold or a die that is typically made from steel or cast iron and can be reused for several thousand cycles. Because the molten metal is poured into the die and not forcibly injected, permanent mold casting is often referred to as gravity die casting. Okay, but anyhow, that's permanent mold casting, where you just pour the molten metal into. Now, obviously, the molten metal can't be the same metal that the die is made out of. So these would have to be, what? Non-ferrous materials, because non-ferrous materials melt at a lower temperature. Permanent mold casting is typically used for high volume production of small, simple metal parts with uniform wall. Yeah, like I said, non-ferrous metals are typically used in this process, such as aluminum alloys, magnesium alloys, copper alloys. However, irons and steels can also be cast using graphite molds. If you ever played with graphite, your pencil lead and stuff like that. And we'll talk about that when we're doing our EDM and stuff like that. Common permanent mold parts include gears and gear housings, pipe fittings, other automotive and aircraft components such as pistons, impellers, and wheels. All right, and it kind of shows you. And it's got this part in here, the core, so you got the hollow cavity there, especially if you're making a piston. You don't want that to be one big solid piece. That'd be a heavy piston, wouldn't it? If you've looked at a piston, this inside part's hollow. It's only as thick as it needs to be to withstand the force of the explosions from the engine, where you put the gas and air mixture and then the spark plug and all that. Alright, so there it is. There's more of a schematic, but I mean, that's kind of what it looks like. Slides back and forth to open up the molds, pop out, eject the part, and then comes back together again. You pour your molten metal in there. And there they are. And see how it goes in there. There's the sprue, comes down a little extra, then comes here, the gating system. What they found out with round parts, and that's what we had to do with our round wheels for the plastics too. If you just have one gate that everything comes in, it doesn't work as well. If you have two like that, one will go this way, one will go that way, they'll meet up there, and that way it'll fill up the wheel quicker before the molten metal cools, and then you only get a half a wheel. All right, and then it just shows you molding temperatures for these aluminum alloys, up to 1450. Copper alloys, gray iron, it's just 2475. If you look at steel, it melts about, what, 6,000 degrees. So, big difference. So that's why the steel molds can handle this. Lowering temperatures here. So again, the process capabilities, the finish, again, the mold material, the mold condition, coating, proper gating, adequate venting of the gases. You don't have any water in there too, so it causes explosions and gives you a rough surface. All that good stuff, excuse me. Let's see what else. Different coating materials, sodium silicate, whiting, fire clay, metal oxide, soapstone. Remember, that was the stuff we use to write on metal that you can see when it's dark, so when you're welding. Talc, like where you get talcum powder, right? Mica. Okay, minimizes thermal shock, prevents metal mold contact from each other. Okay, so it's kind of a mold release. And you can either spray them on, brush them on, or you saw how they just, there's like this bag, like let's say if you took a nylon stocking and filled it up with that talc, and that way you can just sprinkle it like that. So permanent mold casting, molten metal is introduced under gravity or low pressure, often uses close grain cast iron as the mold material, can produce good dimensional accuracy and smooth surface finishes. Castings have reasonable strength with low porosity. So, we don't have a lot of air pockets in them and all that. It's not real porous. Complex or regular shapes are difficult to produce with this. Then we get into investment casting, a process in which molten metal is poured into a preheated ceramic mold, producing a casting which may have intricate internal or external features with little or no draft. Again, that means we're going to probably break up these molds. When they're making specialty rings and jewelries, it's all done investment casting. I mean, the ancient Egyptians did this. This is like one of your first casting processes. There it is. Investment casting is one of the oldest manufacturing processes, dating back thousands of years, in which molten metal is poured into an expendable, ceramic mold. The mold is formed by using a wax pattern, because it's easy to carve wax or whatever you're making, or make a pattern, a mold, to make your wax pattern molds. And then you can make as many as you like. A disposable piece is in the shape of the desired part. The pattern is surrounded or invested into ceramic slurry that hardens into the mold. Investment casting is often referred to as lost wax casting, because you're going to heat up the wax, because the wax pattern is melted out of the mold, when it's in an oven. And then you pour it out, and then you have a hollow cavity. So the lost wax processes are 1-to-1. One pattern creates one part, which increases production time and cost relative to other casting processes. But think about it. It's real easy to carve wax and make a cool looking ring of any type that you want. However, since the mold is destroyed during the process, parts with complex geometries and intricate details can be created. So we don't have to worry about a draft angle. We are not, the pattern actually is melted out, the wax. So you really need to make a mold to make these expendable patterns. All right, investment casting can make use of most metals, most commonly used aluminum alloys, bronze, all this stuff. This process is beneficial for casting metals with high melting temperatures that cannot be molded in plaster or metal because obviously you do damage to the molds. Parts that are typically made by investment casting include those with complex geometry, turbine blades, or firearm components. High temperature applications are also common, which include parts for automotive, aircraft, military industries. Mold creation. This pattern tree is dipped into a slurry of fine ceramic particles coated with more coarse particles and then dried to form a ceramic shell around the patterns and gating system. This process is repeated until the shell is thick enough to withstand the molten metal it will encounter. The shell is then placed into an oven, and the wax is melted out, leaving a hollow ceramic shell that acts as a one-piece mold, hence the name lost wax casting. So again, this time your pattern stays in there. You don't have to remove the pattern. That's why we can just pour that ceramic slurry around it and let that dry, heat it up. Then we heat it up in an oven, and then that wax melts, because, you know, it doesn't take much for wax to melt. I mean, you leave it out in the hot sun, it'll melt. And so then you can take it and then pour out that wax, and then you have a hollow cavity. So the mold is preheated in a furnace to approximately, 1800 degrees Fahrenheit. And the molten metal is poured from the ladle into the gating system of the mold. Filling the mold cavity, pouring is typically achieved manually under the force of just gravity, but other methods such as a vacuum or pressure are sometimes used. And then you let it cool, and then after the molten metal is cooled, the mold can be broken and the casting removed. The ceramic mold is typically broken using water jets, but several other methods exist. Once removed, the parts are separated from the gating system by either sawing or cold breaking, which I've seen this done where they use liquid nitrogen. Anyhow, yeah, watch your hands. So this is showing you here the mold cavity. And they're pouring the molten metal in there. Remember, this had wax in there that they melted and poured out and left this cavity. And then since you're going to break up the mold afterwards, because it's just that refractory mold, then you don't have to have any draft angle on this. You can make it exactly like you want it. The slurry tank, the sand bath, the bake oven, some of the equipment involved there. There's your wax pattern, and then they put that ceramic shell, spray that around it or dip it in there. The robotic arm, I've seen that. And then there's your casting cluster that has that ceramic shell. Oh, I'm sorry. There it is with the ceramic shell, excuse me. Then there's all the 4 different parts, I guess. And there is the sprue, the gating system, all that. So then they have to cut all that out. And they can reuse that again. But that's your finished part. And they're all clustered around this one gating system. Before, then you pour it, and then you can make fine, intricate parts, nice rings, jewelry, you name it. And there's a ceramic shell mold, and there's a solid flask mold. So these are for large parts, high melting point. These are for high production, small parts. Just depends. And then here it is all set up a little more automated. Pattern loading, hardening chamber, slurry tank, fluid bed of the stucco sand. You got it. Again, you don't have to worry about draft angles. Pattern will be destroyed. This kind of shows you. Here's our wax gating system. Let's say this is not blue wax, but let's say it's whatever color, shade of wax this is. the runner, the sprue, the whole 9 yards there. Then you put it in that ceramic slurry. Then let that set up in the oven, and then heat it up some more, and then you can pour out your wax patterns, and then heat it up some more to make sure. And then what? Then you can just break these hollow ceramic shells, and inside you should have your metal parts, which then you'll cut off, and then you can remelt this gating system and reuse that. And for patterns, they can be wax. Another thing is what they're doing now is they use polystyrene foam. You put that in there, and when you put molten metal in it, the stuff vaporizes. We did that in college, good old Buff State where I'm from, and that worked great. So you could just cut, you know how easy it is to cut foam. You can just use one of those heated wires and cut all your foam, get the shape you want, and just throw that in there, and you're good to go. So it's even easier than playing with the wax. Or then they're saying, you know, if this is something, obviously, an industry thing, they wouldn't want students playing around with mercury, right? You get mercury poison. Plus, it's super cold, negative 70 degrees Fahrenheit. So, but again, very limited use for specialty things, high dollar things, but have to be perfectly made. This will give you a perfect pattern, frozen mercury, because it's a liquid. And then it just shows you yield point. Again, what's our lowest? Is cast steel at 55. Brass 65, magnesium 80 to 90, aluminum 80 to 90, cast iron 85 to 85. It's amazing the difference between, well, I guess that's why they call it cast iron. It casts so well. Steel does not. Cast steel does not. So yeah, you look at that, and that has the most, 1/4 of an inch shrinkage. Shrinks the most. So, and your yield percentage is really bad. Alright, so again, investment casting produces intricate detail and close dimensional accuracy, uses wax or plastic patterns, requires little or no draft. Patterns can be clustered to increase production rate, and patterns are melted out of the non-reusable ceramic patterns. Then we get into plaster mold casting, process in which non-ferrous molten metal is poured into a non-reusable shaped plaster mold and held under. Now again, plaster can withstand temperatures only up to 2200 degrees, but that's a lot. That's pretty good. We made some plaster molds, castings in our ceramics class. And plaster, man, if you have a nice shape, it conforms perfect. It's a real fine grain. So those molds were just smooth as glass. So it gives you, I mean, when you're done, you don't have to do any machining. That's the beauty of it. So anyhow, it utilizes gravity to feed, and plaster's cheap. You know, it's part of the gypsum and sheetrock thing. So anyhow, it uses gravity to feed molten metal into a non-reusable plaster mold. It's limited to non-ferrous metals because of the temperature. Can only withstand up to 2200 degrees, and steel, again, I'm saying is close to 6000 degrees, so that's not good. Produces minimal scrap material, can produce thin walled sections, complex shapes, gives you unbelievable detail, fine, fine detail, very smooth surfaces. Then we get into die casting cold chamber. There's die casting cold chamber, and there's die casting hot chamber, apparently. A metal shaping process in which molten metal is forced into a reusable mold and held under pressure until solidification occurs. Alright, so we look at this, and so because it's cold chamber, it's not shooting it all at once, because these are for hotter temperature type metals, and so you have to pour it with either a ladle or a crucible, but usually it's fine detail, so it's smaller, it's a ladle. So die casting is a manufactured process that can produce geometrically complex metal parts through the use of reusable molds called dies. The die casting process involves the use of a furnace, metal, die casting machine, and die. The metal, typically a non-ferrous alloy such as aluminum or zinc, is melted in the furnace and then injected into the dies in the die casting, or it's poured in there. And it's showing you in there, the hot casting can do the whole thing, where it has its little pump, pumps the hot metal in there, but it has to be at lower temperatures. Because if not, if it gets too hot, it ruins the pump. And so this one would, the metal that they're using, so they have to pour the molten metal in there with a ladle, and then, then it's injected in there into your mold, like an injection molding machine. And there you go, and the two mold halves. Then the mold halves come apart, and then the part falls out. Uses pressure to form molten metal into a reusable mold. So remember, the other type of casting did not. Okay. Produces good dimensional accuracy and excellent detail. Requires minimal machining. Typically, it's usually fine the way it is. May produce a small amount of flash, if things get out of kilter, out of whack. Leaves the small ejector pin marks, but that's just, you see them because they have to have ejector pins later that pop it out of that mold half. So you're going to see the little, very small, fine tolerance where those little cylinders come out to push that piece. So it's going to go in there a little bit, possibly. And here's the extra flash on these round pieces. I guess they'll have to cut off. There's the sprue if they're making a bunch of these. And then there's the finished part. Now, if it's done right, you may not need all of that. Then we get into the hot chamber. Again, this is for lower melting temperatures, metals. A metal shaping process in which molten metal is forced into a reusable mold from a hot chamber, then held under pressure until solidification occurs. Here's the plunger. Here's our melting pot here. It's got a little gooseneck that goes in there. And it pumps it actually into there. So with the hot casting. So hot chamber machines are used for alloys with low melting temperatures, or they'll ruin the pump, such as zinc, tin, and lead. Although we don't use lead as much, do we now? Because again, lead, mercury, those are not good for human beings, are they? The temperature required to melt other alloys, aluminum, brass, magnesium, it's a hotter temperature. So that would damage the pump and would just ruin the machine. So if you have to do aluminum, brass, or magnesium, we use the cold. Okay. If we're using zinc, the pot metals, tin, lead, we can use hot. It's quicker, it's better, it's easier. But again, you don't have to worry about having to pour the molten metal in there with a ladle and all that stuff. So again, that's the difference. Very high production rate compared to the rest of them. That's the major thing here, and these are pretty much similar to the other ones. And that's it, and that was lengthy. I'm sorry, I apologize for that. Let me get rid of all this good stuff here. All right, that's all we have. There will be 2 quizzes, like I said. One is first on all the different nomenclature, all the different names and parts. And the other quiz are on all the different types of casting. All right, so we look at that. Whether it's the sand casting, the no-bake, know what the difference is there. Again, that's just a quick setting resin, doesn't have to be baked in an oven. Then we get into the shell, where you do have to cure it, but you put it in this dump box, and the heated actual pattern, and then that material, that resin, it's not a liquid resin, it's in powdered form, with the sand, and when it gets to that hot, exposed to that hot pattern, it heats up and then it cures. That resin binds and cures that sand together. But it only goes as far as that heat can come out, depending how long you let it go, you know, the amount of time. And then you have the vacuum material. So you don't waste as much here, because then you can use green sand behind that, or whatever you want to use, something inexpensive. And then what's the other ones? Permanent mold. What is our permanent mold here? Where was it here? I was looking for. Sorry, I was looking to make sure it was in this slides. I could have sworn I said it. Yeah, permanent mold castings, like die casting, uses a metal mold die that is typically made from steel or cast iron. Okay, except for it's not forced in there under pressure. You saw the other one injected it, plunged it. They pour it with the ladle and plunge. Here, usually these two halves just come together, and then you just pour it in there. So that's the difference between permanent mold or permanent die casting versus cold die casting and hot die casting. I know they get all kind of blurred there. I don't like the way they did that, but that's just the way it is. Just trying to think if we had anything else on that. No, I guess that was. Yeah. Then we get an investment casting, and you're going to invest what? You're going to invest in your pattern. You're going to lose your pattern. It's going to melt out of there. That's either wax or it could be foam, whatever. But again, it's a low-cost thing, and then plus the wax, you can pour it out, and then you can reuse that wax again, melt it, and make another pattern. So you're not really wasting anything. And styrofoam's cheap. You know, we make styrofoam cups out of it, so it's not a big thing. All right, then we get plaster. Like I said, plaster, the only drawback there, it only can withstand temperatures up to 2,200 degrees, or it cracks and breaks apart. But man, that plaster gives you such a smooth glass-like surface. It's nice. So that's the beauty, and plaster's cheap. Then die casting, we said cold chamber. It's like our permanent mold. Only here, it's actually held under some pressure. So we pour it in here, but then it injects it. There's the injection unit. That's the difference between the permanent mold die casting and then this cold chamber die casting. And then the hot chamber, again, is for lower temperatures. And I believe that's it. 78 slides. That's a lot of material, isn't it? Okay, well, make sure you study, go over this, because those quizzes, you only have so much time, and you'll run out of time. I've been seeing a few people get 2s and 3s and 4s, and I see they're getting better now that I gave you a little more time. But I hope that's not just because you're looking them up. I hope that's because you're actually trying to learn the material and study ahead of time. So anyhow, that's all I have this time. You'll see 2 quizzes pop up for this one, and we'll be in good shape.